This tutorial explains the benefits of a process that maximizes the values of your environmental data. There are two main reasons you need this data management process. First, when regulators, NGOs, local groups, and others allege that an operation or project harms the environment, their claim is always based on data. Specifically, the data you collect for baseline studies or permit compliance monitoring. Second, environmental regulations are written to demonstrate to the legislature that the agency is complying with the relevant statutes. This is good for them, but may not be in your best interests. For example, a stormwater discharge permit might require only 1, 2, or 4 water samples for chemical analyses each year, while a group opposed to your operation claims that your discharges degrade the receiving waters. While you can demonstrate that you complied with all permit conditions, you still need to try to prove that you did not adversely impact water quality. While no one can prove a negative, refining your environmental data processing system can allow you to refute these allegations of harm. The 5-step process I'm presenting here has been highly effective in avoiding and resolving environmental issues. This tutorial's focus is on the Clean Water Act, specifically on stormwater discharge from permitted operations. The objective of the CWA is to restore and maintain the chemical, physical, and biological integrity of the nation's waters. To demonstrate that regulatory agencies and the regulated public are complying with this objective requires data, information, and knowledge. Data are always incomplete, spatially and temporally, yet almost always the available data are adequate to avoid and resolve concerns. Appropriate statistical models fit to the available data produce information. Interpretation of the analytical results using ecological, hydrological, geomorphological, and other scientific theories convert information into knowledge that can be used to inform decisions. As a side note, I need to mention that data, information, and knowledge apply to all environmental laws and not just the CWA. In all environmental regulatory situations, data are the key, the foundation upon which everything else is built. Peter Drucker was a management consultant, educator, and author whose writings were highly influential to modern businesses. One of his most important statements is highly applicable to environmental regulatory science. That is, you can't improve what you don't measure. This is a critical point that should motivate everyone whose business depends on environmental data to pay close attention to how it's collected and processed into information and knowledge. The way to do this is the subject of this tutorial. When you finish this tutorial, you'll know how to strengthen your stormwater management process that benefits you and your company. It's important for you to understand that you're not making a one-time purchase, but investing in knowledge and a program that continues to increase in value as you accumulate more data. Most importantly, understanding the process and implementing it consistently will better prepare you for whatever turns out to be the new normal as the economy slowly recovers from the current massive disruptions. Now on to the details. The mechanisms regulators apply to manage stormwater discharges separates point source and non-point source pollutants. Point source contaminants originate from a discrete area, such as a manufacturing facility or construction aggregate mine, that are carried by stormwater runoff to a single outlet into a receiving water body. Point source pollutants examples include dissolved metals, dust, solvents and processed chemicals, sediments from bare earth at mining and construction sites, and thermal waste from power generation and food processing facilities. Non-point source pollutants originate from diffused surface and shallow groundwater runoff of agricultural lands, eroded soils from an unvegetated ground, urban streets, highways, precipitation, aerial deposition, and lawn care chemicals in residential areas. Regulators will require monitoring of receiving water quality for compliance with the conditions set forth in their permit. There are two types of permits. For point source discharges, there is the National Pollution Discharge Elimination System, NPDES permit. Frequently, entire industry sectors can be covered under a statewide general permit. When the agency's general permit qualification criteria are not met, the facility operator must obtain an individual NPDES permit. Point source discharges tend to be comparatively easy for regulators to define compared with non-point source discharges. Non-point source discharges originate from roads, fields, forests, and other areas not controlled by a specific commercial or industrial facility. All are diverse sources, and this results in difficulties for regulators and the regulated public. The regulatory mechanism for non-point source discharges is the total maximum daily load, TMDL, for a specific chemical in a defined reach or an entire river network. This maximum concentration load is then allocated to point and non-point discharges along the defined range. For both of these management approaches, the only way to measure the status of a receiving water body's chemistry is with data, and you, as a discharge permit holder, are responsible to demonstrating whether your operations affect water quality. The process for doing this is implementing the 5 steps that maximize the value you gain from permit compliance monitoring. A major component of the natural world, including aquatic ecosystems, is variability in space and time. Unfortunately, measuring and quantifying variability is rarely part of environmental regulations, particularly when those regulations define how data are to be analyzed. Yet, because the history of regulatory data analysis started with an engineering mindset, when analytical models are mandated for use in environmental regulatory programs, they are usually deterministic. That is, the model predicts ecosystem responses based on a set of fixed equations believed to describe all ecosystems of that type, and all compliance criteria that consist of a fixed value fail to account for uncertainty in measurement, analysis, or natural variability. Knowing that ecosystems are variable and not fixed, predictable, deterministic, you need to follow a consistent process with your environmental data in order to maximize their values. In C-suite business terms, you are acting to maximize your ROI, or return on investment, in baseline and compliance monitoring data. The 5 components for processing environmental data are collecting, storing, analyzing, interpreting, and using. These steps convert raw data into information, which is then turned into knowledge. The knowledge can then be used to make well-informed decisions about water quality, your operations, and compliance with the CWA, CERCLA, or other environmental laws. Compliance monitoring requirements are defined in each permit. They specify the water quality constituents that are to be measured, the frequency of measurement, and often the sampling locations. Some permits also specify the model applied to chemical laboratory results. These requirements meet the agency's need to demonstrate their compliance with state statutes, but they do not provide sufficient data to demonstrate if your discharge impairs receiving water quality. General NPDES discharge permits cover an industry sector across the entire state, so there is no mention in the permit of beneficial uses in the vicinity of any individual permit holder. Because restoration and maintenance of the water's integrity must be determined by measuring constituents meaningful to site and time-specific beneficial uses, these minimum monitoring criteria do not meet your needs when you are challenged on the effects of your stormwater discharges. This is even more important when your operation is subject to land surface sheet flow of stormwaters from your operational area into receiving waters. What are the beneficial uses of the stream or river reach during and after specific storm events? Are the observed discharges or the observed changes in constituent discharges the result of natural variation, or is the runoff of the constituent beyond the range of normal variability? Well-informed permit holders can answer these questions by collecting more data than the minimum defined in the permit. To determine whether your stormwater discharges have any adverse effect on receiving waters, you need to compare concentrations with those from water collected upstream about the same time, earlier in fact. When you have a water sample collection event, visit the upstream reference location first, then collect samples within your discharge reach or at the outfall of your point discharge. The upstream concentration represents ambient water quality, and that water will flow past your discharges by the time you collect there. Because you will compare water chemistry at 2 or more points, you need to record the geographic locations, the coordinates, of your sample collection sites. This is done only once and allows all future sampling events to be at the same places. This consistency is needed for you to understand how stormwater discharges from your operations affect the environment beyond your control. A good model for your environmental data collection records is provided by Oregon's requirements for data submitted to the Department of Environmental Quality for incorporation in biannual reports required under Sections 303B and 305D of the Clean Water Act. These criteria to be collected for an example record is the location of each monitoring station in latitude and longitude and the reference datum, example NAD 83, which is the height of the site above some base level. The water body name and description of the monitoring location. The date the sample was taken. The parameters measured. The measured result of each parameter. The unit of measurement. The method used for measurement, including method detection limits, MDL, or reporting limits, RL, when applicable. Name of the person collecting the data. The measured result, unit of measurement, and lab parameters are entered after results are returned by the analytical laboratory. Geochemistry is more than rocks. It's also the chemistry of surface and groundwaters, sediments, and soils. Stormwater regulations focus on surface waters, while water quality is affected by the chemistry of the other media too. Many factors affect the concentration of pollutants in water. Among these are temperature, pH, and adsorption-desorption on sediment particles. Comparing a concentration from your sampling event with a one-size-fits-all maximum says nothing about your stormwater management program, nor how your operation relates to ambient water quality or the designated beneficials of the receiving water. I want to make an important point about your stormwater data management processing. It is not a research project that requires a large investment of time and money, but because every permitted operation is different, and so are the adjacent receiving waters, you need to expand your efforts beyond the minimal permit requirements so you can understand the relationships of your activities with the local environment and provide a technically sound and legally defensible basis for making operational decisions, as well as defending your program to regulators and others if necessary. This means going beyond the minimum and recording data of potential explanatory variables such as weather, hydraulics, and physical factors at your collection location sites. Many companies store their environmental data on spreadsheets because the tool comes with the software they buy for general use. While spreadsheets are useful for business and financial data analysis, they are the wrong tool for storing environmental data. My strong recommendation if you use spreadsheets is to stop doing this. Replace your spreadsheet with a database as part of maximizing values in your environmental data. A spreadsheet is a digital accounting ledger, an electronic version of paper accounting worksheets. It was created to let people store their accounting data digitally, so it is possible to create tables in a spreadsheet. This is one reason some people believe spreadsheets and databases are interchangeable, while in reality they aren't. There are similarities between spreadsheets and databases. Both can contain a large amount of tabular data and can use existing data to make calculations. And neither spreadsheets nor databases are typically used by a single person, so many users will work with the data. The difference between the two forms of data storage is in the way these characteristics are implemented. In a spreadsheet, every cell is treated as a unique entity. It can store any type of data: a date, a numeric value, a string of characters, a formula referencing other cells. While we can assign a data type to a column, it does not prevent us from entering a different type of data in a cell. These are not true for databases. A database consists of tables, and each table contains only one class of data. For example, sample locations, parameters to be measured, sampling events, and results. Each table column holds a single data type: dates, strings, numbers, Boolean or true-false values. Data not of the column's type is not allowed to be entered. The database rejects it when you try to save the entry. This feature prevents inadvertent mistakes. For example, in a field containing date values, should you try to insert a string, the software will show an error, and you will have the chance to correct yourself. This won't happen in Excel. If you insert a string in a column with date values, you wouldn't obtain an error message, and Excel will store the string value. Each table row holds data for a single instance of that data class. For example, a table for surface water samples would contain columns for sample identification, collection location, collection date, and a column for each water constituent quantified by the analytical lab. The database features I just mentioned improve data integrity. This means that you can't store different data types in the same column, and it is unlikely someone will mistake a data value for an outcome of a calculation, especially in a large data set. Data integrity is a strong advantage when working with databases. You might think that because a spreadsheet can contain multiple worksheets, you can use each worksheet as for a class of data, then create relations between the tables. Why bother using a relational database? Well, in a spreadsheet, each relation will not be enforced by the software itself, nor will multi-worksheet formula prevent data entry errors or allow you to query your data for complex relationships among classes. For example, a regulator might want you to show how cadmium concentrations in the receiving waters varied by date and pH. Queries of this type and much more complex ones are what databases are designed to answer. You can use this type of information to evaluate the effectiveness of your stormwater management program and avoid regulatory penalties and remedial actions. Databases provide a stable structure controlling access, permissions, and user restrictions. One person can make a change that is visible to everyone instantly. This feature increases efficiency and data consistency when using databases. Considering data integrity and data consistency using databases eliminates duplicate data since each is entered only in a single table when it is used by multiple other tables. This is another way to save time and effort while increasing efficiency. If there is a change, for example, the name of a sampling location, you need to make that change in only one place for it to be seen everywhere. Columns and tables can have constraints defined. These limit acceptable spellings and the choice of options that can be applied. For example, a monitoring table only surface water, groundwater, or air for temperature measurements. Spreadsheets provide a wide range of data analyses at the click of an icon or menu item. This is great for business and financial data, but will not provide correct analytical results for environmental data, as I discuss next. Database management systems have functions for descriptive statistics such as average, range, maximum, and minimum, but leave analyses to other software. It's up to the user to decide which software is appropriate for their data and which models will answer the questions asked. I've focused on some of the advantages of your using a database to store environmental data because it saves time, effort, and money while greatly reducing errors when converting your raw data into information. When I started my consultancy, I created a database for data relevant to client projects. Now I've created a single-user version which I call OpenEDMS, Open Source Environmental Data Management System. It's available to all who want it at no cost, ever. The package contains the schema, the tables, columns, data types, and constraints for a relational database management system called SQLite 3. Constructions on where to download the database, it's also free and open source, and how you can use LibreOffice's base or Microsoft's Access for front ends, the user interface, and a testing database for you to practice. Think of OpenDBMS as an IKEA flat pack. You get all the pieces and assemble it to suit your specific environmental data needs. Existing tables store information on data collection, locations, biota, geochemistry, microbes, physical characteristics of the water body, and weather. Use whatever's appropriate for your needs and add to it to cover more data categories. An important point to remember is that environmental data are observational, not experimental, so they require different analytical models. Analyzing environmental data, especially geochemical data, is challenging because the models most familiar to regulators and others do not accommodate the constraints of the data. Examples of geochemical data constraints include concentrations cannot be less than 0. This is important when we look at the distribution of concentrations spatially or temporally by the frequency of each measured value. These frequency distribution plots show the pattern of concentrations and need to be associated with an established probability distribution for us to calculate summary statistics such as the most common or expected value and the variability of the measurements. The familiar bell curve of the normal distribution will result in incorrect answers because, by definition, the normal distribution has a mean of 0, so half the values are less than 0, and we know that chemicals do not have negative concentrations. Another constraint is that toxic chemicals such as metals and organic compounds are most commonly detected at very low concentrations if they can be detected at all. Dissolved metal ions and organic compounds have minimum detectable concentrations specific to the analytical laboratory equipment, the chemist running the analysis, and the ion or molecule of interest. Below this value, we cannot separate the signal from the electronic noise of the instrument. And above this level, there is a gap below the concentration that can be quantified with absolute certainty. It is common for a data set to have 50 to 80% of the lab results reported as below method detection limits, non-detected, or censored, depending on how the lab describes it. There are 4 ways to mishandle these censored data. Ignore them, set all equal to 0, set all equal to the reporting level, set all equal to some percentage between 0 and the reporting level. When we think about this, it makes no sense to do any of these. Ignoring them means that we've lost important information. If we don't know the toxin is present, then we cannot assume it has any negative effects on biota, including humans. Setting them equal to 0 badly skews the most common value, the mean, to a lower value than it really is. On the other hand, setting all measured censored values to the lab's reporting level badly skews the mean higher than it really is. Setting all values to some arbitrary number has 2 fatal flaws. First, it assumes that all censored observations have the same value regardless of place or time. This is an unrealistic expectation. Second, censored values mean we cannot determine whether the chemical is present in the sample, and if it is, we cannot measure its concentration. Therefore, any number you pick is as meaningless as any other number, and they all distort the frequency distribution of the data, rendering it useless for making regulatory decisions. When concentrations are plotted, some values may be very high and exceed the arbitrary maximum limit. That these values typically are less than 1% of all measurements does not mean that they are beyond the range of inherent natural variability, nor that they were sufficiently abundant to impair the beneficial uses at that time and place. In any sample of stream or river water, there likely are hundreds or thousands of inorganic ions and organic chemical compounds. The few that regulators want monitored do not describe the entire chemical composition of the sample. Whether 1 or 2 of these constituents impair a beneficial use cannot be determined when isolated from the interactions with other compounds, such as synergistic effects of multiple chemicals, temperature, pH, or oxygen levels. Because it is so common for toxic chemical analyses to be below the analytical laboratory's method detection limit, it's important to understand how these censored results can be validly analyzed. There are 3 robust statistical models suitable for these data. The easiest model for every non-technical decision maker to understand is survival analysis. Survival analysis was developed for use in medicine and manufacturing, in the latter case for determining the mean time between failure of a product. The development of a hypothetical new light bulb is a simple example. The company that designed and built the bulb needs to learn if the MTBF for their new product is greater than existing competing products so they can decide whether to put it in production and sell it profitably. How do they do this? In their testing lab, they set 100 light bulbs in sockets and turn them all on. Every 12 hours, a lab tech notes the time since the start of the process and the number of bulbs still working. They do this for a week, 168 hours, then end the experiment. They have 6 bulbs still working at the end of the week and have no idea how long each of those would continue to light. The unknown lifetimes of these 6 bulbs are censored data. By plotting the number of lit bulbs at each 12-hour period, they create a curve that describes the time to failure of the 94 bulbs that burned out during the week's experiment. There will be a probability distribution that fits the data they have and represents the unknown fates of the bulbs still lit at the end of the week. Using the mathematical description of the probability curve that fits their data, they can calculate the mean time between failures as the mean of that distribution and also estimate the standard deviation of light bulb life. Censored chemical concentration data are the mirror image of the right censored MTBF study. That is, it's left censored. The analysis works by mathematically flipping the chemical data from left censored to right censored and using a survival analysis model to fit a frequency distribution curve to the known concentrations, just as the light bulb manufacturer did with their product. Once we fit the curve to the data, we can calculate the mean, standard deviation, skewness, and other properties of our known and unknown data. This is powerful stuff that makes use of all the data you've collected. The results are technically sound and legally defensible because they are based on proven, robust mathematics that makes no arbitrary assumptions about the censored data. Aquatic ecosystems are highly variable, stochastic, and not deterministic. This means that analytical models must incorporate uncertainties in their results. Statistical models all quantify uncertainties since they are based on probabilities. To understand why statistical models found in spreadsheets and taught in university science and business classes don't work with environmental data, it's necessary to look at how these common statistical models were developed. In the early decades of the 20th century, the mathematician R.A. Fisher worked for the Scottish agricultural community on improving farm yields. He focused on oats and designed experiments using small plots, each with a difference of one or a few variables. He randomly planted different oat species at different densities by random assignment to the plots. Another variable was the amount of fertilizer used. To analyze these experimental results in crop yields, he developed the familiar null hypothesis test. This test is based on the frequencies of different results in each experimental plot and assumed that results did not differ by plot or treatment. The now common threshold of 95%, or p less than 0.05, is the threshold used to determine if two samples are statistically different. Well, there are two big problems with this. First, environmental data are observational, not experimental. And second, there's nothing magical about 95%. In fact, Fisher argued strongly against setting a single arbitrary threshold value, but lost that argument to other mathematicians, including Karl Popper. Also, setting a fixed criterion of hypothesis acceptance or rejection is counterintuitive when we look at natural ecosystems such as rivers that change constantly along their length and over time at various scales. Deterministic models such as HEC-RAS, Qual2E, HSPF, and BLM, that's Biotic Ligand Model, not the Bureau of Land Management, define the environment using mathematical equations that relate one component to others in fixed ways. In other words, the equations determine how the environment works. There's no accommodation for uncertainties in measurement or relationships among components in these models. They also demand many categories as input to the models and require constants that may or may not apply to a particular time and place. There was always more than enough contention in environmental regulatory actions that we don't need more by applying the wrong tools when making decisions that cannot be proven correct. Converting the information produced by analyses of the raw data into knowledge is done by interpreting analytical results using ecological, biological, and other scientific theories. These interpretations are often contentious. In litigation, it results in the battle of competing experts, and it can be difficult for regulators and the public to accept because of the scientific basis. The meaning of stormwater chemical concentrations on receiving waters needs to be based on established scientific knowledge of hydrology, open channel hydraulics, and aquatic ecology apply to the beneficial uses for that reach of stream or river. Robust comparisons with previous data from discharge and upstream reference sites should form the foundation for interpreting monitoring results as they relate to the CWA objective of restoring and maintaining ecosystem integrity. There is no cookbook approach to interpreting geochemical data. Each permitted discharge location, the season, storm intensity and duration, and other factors all affect the meaning of the collected and analyzed data. One factor that can improve acceptance of your interpretation of data is by showing whether it falls within the variability of, for example, 95% of all data from that location and similar seasons. There are mathematically correct and robust statistical models that calculate 95% confidence limits of data sets. When a data point falls outside the envelope, it's time to look at the cause. And the reason might be related to the permitted operation, or it might be a rare high value like 100-year floods that occur more frequently than once every 100 years. When measured concentrations fall within the confidence limits, it is most probable that regardless of concentrations, the measured value is within the range of uncertainty and there is no impairment of beneficial uses. This step in processing baseline and compliance monitoring data supports the investment in having an upstream reference site in addition to the locations included in the permit. I refer to beneficial uses and not single value maximum thresholds for assessing whether stormwater discharges impair receiving waters. That's because beneficial uses are the only criteria that can be assessed for restoration and maintenance of the chemical, physical, and biological integrity of waters. This is especially important with permittees in areas of non-point source discharges regulated under total maximum daily loads. Almost 20 years ago, the National Research Council examined the TMDL approach to water quality management and found many inadequacies for which they offered more technically sound and legally defensible methods. One of the NRC recommendations was that states should develop appropriate use designations in advance of specific anthropogenic use of the area. Most states have done this, but other NRC recommendations, such as refining beneficial uses before setting water quality standards so that general terms such as fishable and swimmable are made more reach and activity specific. While it's easier for legislators and regulators to set a single water quality standard, for example, human drinkable water for all waters in the state, that does not make scientific sense nor demonstrate CWA compliance. Rural areas, for example, have streams and rivers which have only wildlife and livestock drinking available waters because there are no municipalities or residences using surface water resources. When specific beneficial uses are identified for streams and rivers receiving stormwater discharges from permitted operations, those should be the standards for interpreting baseline and compliance monitoring data. Using the knowledge and insights you have gained from processing your environmental data is how you maximize its value to you and your operations. Each operator will apply this knowledge of the local ecosystem and the operation's interactions with it to avoid and resolve issues that are raised by regulators and others. While each situation is going to be different and specific to activity, place, and time, common guidelines apply to permit holders, regulators, and litigators. When you understand how your operations interact with receiving water and other components of the local ecosystem, you know whether operational changes are needed. Everyone from senior management down can effectively act to avoid issues and suggest ways for future operations to be done effectively and profitably. Yet, when your knowledge is that current operations are likely to adversely affect the beneficial use of the receiving waters, you understand what changes to make to remedy the situation without fines or other penalties. And when you document that your operation doesn't impair beneficial uses, share this knowledge with legislators, regulators, and other stakeholders to demonstrate your environmental stewardship of the land. When regulatory agencies encourage and support permit holders to apply the process that I've described in this tutorial, they gain multiple benefits for themselves, the natural environment, and society in general. When data have geographic and time attributes, they can be combined to provide statewide perspective of water quality. When stream and water reaches are identified for restoration, there's likely to be available data to guide the process, and the collected data document ambient variability by basin and other areal criteria that help to understand the dynamics of aquatic ecosystems in the state. Environmental, natural resource, and water attorneys gain insights that make their advice to clients more effective. Litigators present technically sound and legally defensible knowledge to finders of fact in language that's easy to understand. Most decision makers, from elected officials to judges and juries, are not environmental experts. Speaking to them in plain English and showing the process that supports the presented results increases appropriate decisions. What I want you to remember is that all environmental regulatory science and issues are about the data. Applying a technically sound and legally defensible process to your baseline and compliance monitoring data provides you with strong support for your position. Incorporating this process and following it helps to make your environmental actions and departments profit centers. If you want more information or answers to questions, you can visit my website or contact me by telephone or email using the information provided here. Thank you, and I wish you good luck.